Hi, this is Rahul. In this video we're going to discuss about membrane materials and modules. A reverse osmosis membrane has a thin microporous surface that rejects impurities, but allows water to pass through. The ability of membrane to reject an ion is not only related to ion size but also to the electrical charge that it carries. Ions of low charge are more difficult to reject. The amount of a particular ion in the total dissolved solids, TDS, content of the water as well as the pressure difference across the membrane are also important. Osmotic pressure is a term related to the chemical bonding of dissolved materials for the water molecules. See this membrane structure carefully because this is help you what I'm gonna to tech you. Some manufacturers list a rejection rate for contaminants which the unit should remove, but others report rejection rate only for the total dissolved solids, TDS, or the rate for a test mixture of salts, higher operating pressure or specific membranes. A rejection of 80% or more is possible in reverse osmosis. TDS content is an important factor. Reverse osmosis membranes made by polymerization, exposed to different solvent composites, have varying degree of surface roughness. As the roughness doubles, the permeate flux also doubles but the rejection remains the same. In this table you can see rejection coefficients and fluxes under different test conditions for a variety of commercial row membranes.
From here I am going to discuss about membrane separation process.
Reverse osmosis membrane have been formed and tested using a large number of different materials. Cellulose polymers such as cellulose acetate and triacetate are the most widely used. However, polyamide and polyurea composite membrane typically have higher water fluxes and salt rejection in row process. The chemical structure of cellulose acetate and polyamide are given in figure. Even they are able to withstand higher temperature and wider pH, 4 to 11, variation. Polyamide membranes tend to less chlorine resistant and more susceptible to oxidation as compared to cellulose acetate membrane. Solutes which are effective excluded by the cellulose acetate membrane are the salts like sodium chloride, sodium bromide, calcium chloride and sodium sulfate, sucrose and tetraalkylammonium salts. The major limitations of cellulose acetate membrane are that it can only used in aqueous solutions and that it must be used below about 60 degrees Celsius. Most commonly available row membranes are divided into two groups as follows: asymmetric membranes, skinned, thin film composite membrane. Asymmetric membrane. These membranes have a thin, -100 nanometers, selective skin layer supported on a more porous sublayer of the same polymer. Dense skin layer determines the fluxes and selectivities of membranes, whereas the pore sublayer serves only as a mechanical support for the skin layer. The thin, dense has the ability to block the passage of quite small solute molecules. Thin composite membrane. These membranes consist of a thin polymeric barrier layer formed on one or more porous support layers, which is almost always a different polymer from the surface layer. These membranes are generally made by interfacial polymerization, a process in which highly porous membrane, usually polysulfone, is coated with an aqueous solution of a polymer or monomer and then reacts with a cross-linking agent in a non-aqueous. More recently, Film Tech Corporation introduced a membrane diamine and trimethyl chloride. These membranes are somewhat less sensitive to chlorine than the PA300 membrane, and single-pass seawater desalination can be achieved.
Thank you for watching this video. Further we will discuss about part 3 of the RO process. Also like my video and share or subscribe my channel.